I got my magic 8-ball right here. Going to do a little demonstration for you. It's all about something that Galileo figured out a few hundred years ago. What an incredibly smart man. He had a question. He wanted to know if he could measure or find the relationship between time and distance if he dropped something from a height. Okay, he wanted to see if he could record how far the thing went in a certain amount of time, but it was really difficult back then. He didn't have really nice fancy cameras and video equipment, so he said, what if I drop something, but I put something in the way? So it drops at a slower measurable rate, and so what he did was he built a ramp, and he built a really fancy timing device too. Whole nother story. And what he ended up finding out was something super duper cool. So what I've done is I've created this ramp, and this ramp is at 5 degrees to the horizontal. Okay, so it's not a huge angle, but it's an angle. And you guys could probably guess that if something starts to go down the ramp, it's going to get faster and faster and faster. The whole idea of acceleration. So acceleration here in Denver is about 9.8, maybe just a tad bit less. Barely, maybe like 9.79563, some, okay, you get the idea. We're going to use 9.8, okay? So, I know how to figure out the component of this acceleration that's going to be acting down the ramp. It's actually pretty simple to do. It's another lesson for another class. But basically, all I do is I take 9.8 times the sine of 5 degrees, okay? And I end up with about like 0.9 meters per second squared. Okay, so that's going to be my acceleration down the ramp. What Galileo found was something remarkable. He found that in 1 second, for example, in 1 second down a ramp, this ball, might travel this far. On this ramp, it's going to travel from here to here, okay? It's going to travel this much distance, all right, down the ramp. What he saw, though, was in the next second, it didn't travel this far. It traveled from here to here to here. It traveled, if this is 1d, 1 unit of distance, it traveled 3 units of distance. He was like, wow, that's pretty cool. What if I let it go for another second? Well, he did. So here, in this 1 second time period, it didn't go just 1d. It didn't go just 3d. It went 5d, 5 times this distance. And if I had a bigger ramp, I could show you that in the next second, it would go 7d, 9d, 11d. Okay, you get the idea. That's cool, but what does that really mean? Well, he thought about it, and he's like, okay, wait, from the very start, right here, from where this thing is going to begin, in 1 second it will go one unit of distance, or one measurement, okay, 1d. In 2 seconds, it's going to go from here, it goes 1 plus 3, it goes 4d. In 3 seconds, it goes from here, 1 plus 3, now I'm at 4, plus 5 units of distance, that's 9. What he found was that the distance the ball travels is proportional to the time squared. The distance it travels is proportional to the time squared. Do we have an equation that represents what Galileo discovered? The answer is yes. Delta x equals my initial velocity times time. I'm releasing it from 0, okay, that goes away, plus 1/2 a, well, that's the rate of acceleration down the ramp, times time squared, right? So delta x equals 1/2 a t squared. That is where that formula really comes from. Let's see if it works. I know Galileo could do it, and I'm not nearly as smart as that guy was. But let's see if we can get pretty close. Here we go. All right. 3, 2, 1, 1001, 1002. 1002, 1003. That's pretty darn close. I may have broken something. We'll see.